So this is both a security talk and a unit testing talk. So I've fooled you all into software quality by making this look like a security presentation. Congratulations. It's a great way to start the morning. What I want to talk about is primarily what firmware developers have to face when it comes to testing and verification. Look at the tools that we already have for driver and application developers, primarily for UEFI. Introduce the concept of host-based firmware analysis, talk about how we use this for techniques like fuzzing, and show some examples of how we build and run test cases with what we have in open source. Oh yeah, of course, because of this conference, this is an open source tool. But first, some of you know firmware very well, some of you are just getting into it, so I want to set a background for what a firmware developer has to deal with today. I've been doing firmware development for an embarrassingly long amount of time, starting out writing assembly code and explaining to people why they should use XOR AX instead of moving AX 0 into AX. Yeah, if you know the reason why, you've been doing this as long as I have. But platform firmware is an essential component and root of trust. We're the thing that gets control after the reset vector. You can have a really fun party between the reset vector and handing off to the OS. So we want to make sure that this is the code that we're expecting to run. It's a low-level component. Many of you are at this conference because you look at the current state of firmware and think, there may be some security issues I would like to inspect. Yeah, that's what every firmware developer is now thinking. Unfortunately, most firmware validation happens at integration testing because it's tested as part of a platform, not as an independent item. So the usual way we do testing is we get the unit, we plug everything into it, and we do some kind of external input, some sort of test harness or apparatus, Frankenstein-looking thing with cables all over it, to test the firmware as a component, not as, okay, well, what makes up the firmware? Dozens, possibly hundreds of little independent drivers that have been written, not always by the same company, not always by the same developer. We put them in a big pile, and if one of them fails, we may not see the side effect of that until way into runtime of the platform. So we're going after functionality and stability, but the way that we do integration testing, you can't really figure out what the issue is with an independent component, whether it's something you developed and handed off to a team for integration, or whether it's something you absorb from a third party or a different open source project. So I look at software release in kind of two ways. When you say you're releasing software, are you releasing doves at the Olympics, or is a bear being released from the zoo? Like, one of these is obviously better than the other. Okay, so our dependency and integration. There are a lot of tools that we use that are focused on integration testing. Some of the folks in the back of the room work on test harnesses. I see you guys. Those are pretty fun. But if you're looking at security, one of the few tools that we have is ChipSec. So ChipSec is essentially an open source framework for analyzing the security of the platform firmware and hardware. Treats them as kind of codependent components. But it evaluates the system condition at runtime, not the underlying code. So ChipSec can tell you, I set the bit correctly. It can't tell you if you set the bit in the most optimal way. So what most people exploit is not the setting of the bit, but it's how you set the bit. So it's really expensive to mitigate issues in integration. By the time you get to integration, you're possibly into what you optimistically are calling a beta, which is probably really still an alpha, but we'll call it a beta just to be nice to everybody. And then you do most of your testing on that. If you find something at that phase, it's way more expensive to go back and isolate down to the single driver than it is to test that driver independently before you integrate it and it disappears into a mass of other code. So can we improve our testing before integration? Well, of course we can. Otherwise, this would be a really short presentation. But it turns out application developers have done this for years. This is not a new thing we're getting into. Somebody in Windows or Linux land will have said, of course I tested my driver in isolation before I give it to the rest of the world, because I'm in an upper level application environment. So I can do cool things like fuzzing. A guy walks into a bar. Two guys walk into a bar. A priest, a rabbi, and a monk walk into a bar. -1 people walk into a bar. XFFF people walk into a bar, right? So there's your edge cases on fuzzing. Now, integration is a guy walks into a bar, asks you what time it is, and the bar burns down. So you still have to do integration testing, but you can do basic things on fuzz testing that just throw garbage inputs. And that, by the way, is how we get most of our friendly little buffer overflows and memory issues. Address sanitizing. So this is another way to detect memory corruption issues, which is another fun way that people try to get into the world of firmware. They'll corrupt variables. They'll throw random garbage to try to force asserts or get you down into edge cases that you haven't fully tested. Code coverage. Did you really test all the code? You have a switch that says on. Did you test it off? You have a switch that uses on, off, and other. Did you test other? You did all the ifs. Did you do all the elses? Code coverage will allow you to look at your test cases and see if they are actually measuring everything that you do. Now, these are very easy to do in an operating system compared to firmware. So, because an application developer will say, oh, I've got this OS layer underneath, and I can use that to expose all of these inputs, APIs, interfaces that I can put into fuzzing. Firmware is existing at a quasi-hardware level, and it's harder to get those pieces in place. So this is something we've run into a lot at Intel. So I'm going to focus more on fuzzing as a test approach. There's tons of other cases that you can do, but it's a 30-minute presentation. So an effective fuzzer will do semi-valid inputs. Something that looks just right enough to be passed on by the program, but hopefully the program doesn't do validation, right? One of the problems that we've had from the mindset of older firmware developers is that this is my trust boundary. The flash part is my trust boundary. Anything that happens in here, I must validate it. I trust all the people involved in it. In the 80s, probably, because there are 6 people at your company. They did firmware. They all sat in the same room. They probably all wore the same polo shirt from the same trade show they went to. But you get up into firmware development now, and I bought a NIC from one company. I got a GOP driver from my graphics company. And then my department has folks in 3 countries. So you can't always assume there's a trust boundary in that. Then we get into the supply chain, and that's a whole different problem. So you have, again, from the OS environment, things like AFL, Peach, libfuzzer that go into, let me throw random inputs at this and make sure that it is trusted before I integrate it into a piece. So AFL, again, is a very security-oriented fuzzer. It works across a variety of operating systems. It's Apache licensed. So it uses compile time instrumentation. Genetic algorithms, I'm not going to pretend to understand that. I got my master's degree a long time ago. But you're trying to find test cases that trigger what they call politely new internal states in the target binaries. In other words, edge cases, stuff you didn't test. And the idea is that you're improving your functional coverage for what you're testing. Peach is more known as a smart fuzzer. So it's mutation-based testing. It takes the cases you build and starts to build its own edge cases around it. So it's going to attempt to do things that you don't think of. I don't know how many of you actually, if you're security folks who deal with developers or developers who deal with security folks, but y'all think differently. Security folks think in a way of, here's this box, and I don't know where to put the crowbar to pry it open. Right? There's a completely different approach for that. And something like a mutation-based fuzzer means that your testing people don't have to think about every edge case. It tries to create them. It tries to create inputs that will trigger edge cases based on what you fed it. It makes a thing called a Peach Pit file, which is an XML file that defines the structure. This is an MIT licensed tool. libfuzzer kind of works off of LLVM's compiler infrastructure. LLVM is very good at adding things like sanitization coverage. So this is coming up with inputs for target functions that are based on this. So this is where you find heap, stack, and global issues, memory leaks. So you allocated memory, you didn't free memory. Assembly code to C programmers, people that have gone from the legacy BIOS to UEFI days. Assembly programmers never had to allocate memory. We were just like, there's memory. It's at this fixed address. Upper level application programmers, people who've been doing C++ for a while, understand these concepts better. So you will find a lot more of these I made memory, I didn't take memory away. I didn't free my, didn't clean up my after myself kind of issues in firmware. All right, these are cool upper level OS tools. Let's try to put them in a firmware environment. So it turns out a couple years ago, some very smart people at my very large Fortune 500 company tried this. The short answer is it's really hard. Getting something that's designed for multi-threaded OS environment down into firmware, it'll work, but it's, the polite word at this time in the morning professional setting is suboptimal. It was not good. Okay, well, let's flip this over. We've already been running UEFI code in simulators. We've got QEMU, we've got commercial stuff that we use at Intel like SIMX. Maybe we do a simulation environment. Well, again, simulation environments are more for simulating a system. So that's more of an integration idea. Okay, well, what if we, well, this is just a driver. It's just a set of APIs. I don't want to see if the code is functional. I'm trying to do edge case testing. I really want to test just the ins and outs. Again, I'm not looking at, can I set a bit on a piece of hardware at this phase of testing? I'm looking at, does the API I've established in this firmware interface do input and output correctly? Does it, check who's coming in the door? They open up the velvet rope at the club for the right people. So again, what we're trying to do is just test this native UEFI code. If it's not going to touch the hardware, then why don't we just stub it out and make it so that these existing test apparatus that work for the OS work on this individual unit test. Not going to find 100% of the problems, but you will find that stupid piece of code that doesn't call MDE package correctly. So this allows UEFI code to be tested on the developer system, hence host-based, not target-based. So same smart people went off and made a tool called Host-Based Firmware Analyzer. This has been out in open source for a bit. We announced this at RSA 2019. We put the first code up in a repo, I think, in April. It's in the EDK2 staging repo, links at the back of the presentation. But the idea is that we've created a set of interfaces and a way to stub out EDK2 code that allows you to run existing tools, including fuzzing and address sanitization. And we create a database of unit test cases, which a lot of the unit test cases we're using are just up in the repo with everything else. And we're using, really what this is designed to do is say we're not reinventing the wheel on this. Other people have done fuzz testing, address sanitizers better than we have in firmware. Let's just go take that stuff and use it on what we're doing. So it's not a tool, it's really more of a framework where you can run best-in-class tools from other people. If something else comes along that does a cool thing we're not doing, there's a way to stub that out and put it into this framework. So again, we're moving some of the unit testing to an OS environment. This doesn't get you off the hook for testing your own code on a platform, but it does come up with cases that you would have trouble isolating on a platform when you encounter them. So OS-based tools typically have native code coverage support. We can take advantage of that as well. The question is, what can and can't be tested in this environment? The stuff that is optimal for testing in an OS environment are features that are based purely on software logic, not UEFI or architecture dependencies. So I'm going to pass my boot logo as a BMP into the BMP parser so that it displays the logo on the screen. You get a little spinny wheel underneath it when you start loading the OS. Okay, well, people have abused that. There's no cases where people passed in a BMP and it tried to execute code. So that's one that doesn't depend on anything in the hardware. It's purely software logic. That's a great case to test in this environment. UEFI code that has good modularity. Actually, I know some of you in the audience will be shocked. People can write really good modular UEFI code. Not everyone, which is why we still have unit testing. But things that follow more of the boundaries we set up in EDK2 that are more portable pieces of code. And some features with hardware dependency, so MMTR settings, PCI Express bus access, USB hardware, that's not going to work great in this environment, but they require some code steps to eliminate dependencies. So you still want to be able to see if your input gets passed correctly to a function that sets an MTRR, because that's something that's abusable. but don't expect your system to set that MTRR in a host environment. In fact, please make sure you don't do that because I don't want to crash your host system. Okay, again, I'm going to focus more on fuzz testing here. There's 7 or 8 different packages that you can put into host-based firmware analysis or HBFA. But again, bad way to wake up is to have me read documents at you. So let's just look at fuzz test case design. So within the framework of HBFA, you have a test case folder called test case. It sits under a directory that is obviously for fuzzing. There's a toolchain hardest library that goes into the library class. If you're not familiar with EDK2, we use INF files to define the basically the needs and wants of the compiler for making a .EFI file that is spit out for that particular component. We're not looking at the DEC or DSC things that you need to build an entire firmware image. We're just looking at the DSC and INF files that you need to build one individual component. There are 3 functions that need to be implemented: get max buffer size, run test harness, and there's an optional fix buffer. We'll assume that your program is intelligently and obviously named test YYY. Never name real code, that sort of thing. But once you have created these 3 functions for this component, then you add an entry in the INF file to use the host fuzz test case package. This, of course, is just me reading a portion of the wiki. Yes, we did actually document some of this stuff. Right now, a lot of the documentation is in one of the developer staging branches, but we're folding this back into the main documentation for HBFA. Okay, here's us steering at code. Ooh, this really doesn't look that impressive when I'm developing, presenting to a room of developers, but it is something you can look at. The slides will be available along with the video on the OSFC site. But again, what we're doing is roughly initializing a test buffer, running that test case, and cleaning up after ourselves because we're good adults. Again, you have to do 3 additional functions. This is why it's great for unit testing. This is terrible to do in integration. We're not going to leave these things in when we actually deliver our code to the integration team. But we do want to make sure that we've got this sort of repeatable set of functions that can be dropped in for stubbing. Once you've done this fuzz testing a couple of times in early development and unit testing, it easily drops out. And then again, there's this additional test partition.c file. All right, so for the case of fuzzing, if we're using something like AFL, libfuzzer, or Peach, we'll basically have an entry point into toolchain hardest function. The fuzzing framework will feed garbage, semi-garbage inputs in. They will trigger the function to be tested. We'll set up the function, record and measure the results, and return a test report. This tool spits out a lot of information. But it's really easy to go through and see where you've got potentially failing cases from the different test tools. There is a GUI way of running the tests. You add HBFA to your packages path. That's part of your EDK2 environment setup. You'll set up the EDK build environment for Linux or Windows. There's a Python script that you run to generate the configuration with a new tool chain. That'll set up the host fuzz test package. It's really hard to read camel case in the morning. And then you run a Python script that starts the GUI, and then the GUI allows you to select the different test cases. This depends entirely on which test apparatus you've installed. You have the option of installing every single thing that HBFA supports or just doing a subset. Test reproductions, again, we spit out lots of data. Failure inputs are automatically recorded by the fuzzing frameworks. AFL, Peach, and libfuzz have a different directory structure. So AFL has 2 main output files or folders. One is for crashes and one is for hangs. So crashes is the, hey, this obviously went off the rails, and hangs is it went so far off the rails that it just tipped over sideways and died. So that allows you to classify different types of inputs, and then inputs have an ID format. Peach Fuzz just has a folder called faults, and any of your detected failure inputs come as some kind of initial action, and they'll be sequentially numbered. And then libfuzzer has an output folder for failure inputs. And again, what you're trying to isolate is this is the input that caused your code to go bad. And then you can go in and see why there's not a validation check for that. It's a Windows and Linux-based tool. For some reason, I'll just read the bottom part. Read the room, Brian, read the room. So GDB can actually be used for going through your test case information. So you can use your standard BRCSNP type of commands to step through. And if you really feel like it, apparently Microsoft Visual Studio makes some tools that are GUI-based, and you can go play with those. All right, why in the world would we do this? Again, integration testing is not a really good way to find security problems. Let's just be honest. Again, because integration testing, we're all focused on the functionality. Our customers like security, but they really get more shouty and yelly about booting the operating system, running applications, speed issues, compatibility with devices. So security is something that we push through our entire development cycle, but you can't have security testing and then integration testing, right? You kind of have to make sure these are all combined. So what this allows a developer to do is quickly execute a variety of tests prior to integration that will find the most common dumb things you did that causes somebody to be able to break in. It's easier to get the crowbar under the box lid if you forgot to put one of the corners on, right? So we're taking existing tools that do this for OS development. Again, one thing that I've learned over time with firmware is the reason we become the happy target for people in security world is because there's a perception that we've done less work on this type of thing than the OS and application people. If you look at the progress in application security over the past decade, applications have become very hard to break. You watch bug bounties go up and up and up. A bug bounty price is an indicator of how hard it is to break a thing. So that's just the invisible hand saying, okay, it's worth more to do this because it's harder. So firmware is kind of perceived as a place they should explore because everybody else is up their security game. So all we're doing is bringing more game so that we are less attractive. It's not that you can't break into the thing, it just takes more effort. Somebody I talked to who works not in this building but for this company told me of a concept of 10 minutes of quality time. If I can spend 10 minutes of quality time with your laptop, what can I do? And if your 10 minutes of quality time, 8 minutes of it is figuring out why this thing doesn't run in the firmware, then they might just give up. If it takes them a minute to get the thing to run, you're the most attractive target on the platform. If it takes 9 of those 10 minutes, you're the least attractive part of that platform. You're not as easy of a deterrent. You're not the person walking home from the bar going, look at all this cash in my hand. You're less likely to get mugged if you have that in your pocket, right? So it's the same kind of mentality. Let's take the tools everybody else used to up their game, run them on our stuff. It's extensible because we don't know what the next tool is going to be. We don't know what the next threat is going to be. We pay people quite a lot of money to think about that sort of thing. So if someone comes along and says, I've got a new cool test method, I came up with a Bitcoin genetic blah, blah startup buzzword algorithm that I can run, cool, we'll roll that in. That'll be the 9th thing we can do in HBFA. This is something we're feeding to the ecosystem. We didn't Intel brand this. It's not Intel registered trademark HBFA, it's just HBFA. If we can only do the testing and replication at Intel and we can't have our customers do that, how can we expect them to secure their platforms? Because we're putting this code out in the open, we're putting this code out to our customers, putting this code out to people who want to write code for our customers or want to replace the code our customers write, depending on your particular firmware approach. So we want to make sure everybody can replicate what we do. So if we say we tested this, cool, you might not believe us. If we say we tested this and here's how we did it, I think that's called science. So that makes a little bit more sense. So really we've introduced this to bridge a gap that we saw in development, which is that unit tests weren't, producing enough security-focused results. All right, homework. I helped write a white paper on this a couple of months ago, and our team has put this code into the EDK2 staging. So EDK2 has a couple of different, or Tiano Core itself has a couple of different projects. EDK2 is the main firmware core development. That's where you get your EDK2 stable tags, what we used to call UDK releases. You have EDK2 platforms, which is code designed for a particular thing. That's what System 76 was talking about yesterday with their Tiano Core for their KB Lake and Whiskey Lake platforms. And then you've got an EDK2 test repo, which this will eventually end up in. But for code that we are like, this is good, but we don't think it's quite ready yet, we put that in EDK2 staging. So that is for things that we think will go to production, but we would like input before anybody relies on this in a production environment. And that's where HBFA is right now. We've had a couple of customers integrate this into their CI environments. And we've had some people who are looking at it, making contributions, but are talking about baking in it once it leaves staging, which we expect to happen before the end of the year. The white paper is good if you have to convince a manager to go work on it. And then all the stuff here, like the evaluation version, the build and run guide, how to run a test case, how to add a new test case, those are all for the development folks. So, and I've got a blog, which is another good thing you can hand to a boss and go, hey, should I be working on this ? And if you want to do real work, don't read my stuff, read the stuff in the wiki. Okay, that is all the slides I got. So we have time for some questions.
Excellent. Can I do any of this stuff on the LVFS?
So that's an interesting question. The answer is probably not. I brought a stunt security person with me if he wants to throw down any of this. Sorry, I called you out so early in the morning. Really, this is designed for code, not for finished binaries. So if you write some cool code that's going to get integrated into somebody's EDK2 project, yes. But I think you would probably be using the same fuzzing tools of the OS layer to check your stuff before you release it. I don't think it's really set up to do binary
There's nothing
analysis.
left in the binary to kind of...
No, because it's a test harness, so we got to wire it up, right? And by wire up, I mean write some dummy functions that don't go into the final code.
So what else can I do?
You already talked to our chipsec people, and it's a loaded answer, but chipsec is still good, again, for the runtime state of a platform. It's going to be an integration type thing, but again, it's going to measure if you left the platform in what you consider to be the most secure state, or what we consider to be secure enough state for what has been released into the world. I think we've already had a side discussion about whitelist and blacklist in chipsec, and if you can build enough whitelist data, then it'll give you an idea, because you're getting an aggregate through LVFS of all of the submissions. And if you're getting signed pieces, you can try to at least, if you don't have only whitelist data, you can say, these are what I know is good. And here's the units or the things that came in that I can't identify. So that's whitelist, and I guess what we call gray list. I don't know, applying a color scale to these things is kind of weird. I don't know if you've got the ability to actually run like a blacklist type of scenario, but that's pretty valuable. But that's going to require on kind of accumulated knowledge. Way in the back. Buffering question, please wait.
So would it be part of the EDK release process? Do you plan to apply that to whole EDK 3?
What we're looking at doing is, so we can't automatically apply this to everything in the tree because it does require some manual work to bump in the different, the three functions I was showing you that do the test instrumentation. So I think in our process, I need some help from my stunt developer in the audience. Are we requiring this in our process right now, or is this kind of still not 100% rolled up in what we do internally? Do we know that?
I think this is a newer tool that we're still becoming more familiar with at Intel. And so I think as we go forward, I think we see more adoption, but I don't think it's required today.
I know that so one thing we're still defining for Tiano Core is continuous integration path, which hopefully the next time we get together, we'll have a cool presentation from Stefano on what that looks like. We're still talking to the community about what the best CI framework is that's most compatible with the community's needs. Just because we're doing something in Intel doesn't mean it's the process that everybody else needs to be using in the open. Either because of like we paid money for some things, or we use one cloud framework and everybody else wants to use a different one. But we are getting to the point where we'd like to do more automatic CI. So, you know, if you check in a piece of code, things automatically happen that do, you know, we can do the dumb stuff like tabs versus spaces, or we can also do more intense things like, could we snap in some of these CI pieces? Microsoft has actually done quite a bit of work with HBFA, and I think they've got something in their internal Project Mu framework that is using this as part of their CI process.
Just wondering if this were to look for CVs in EDK2.
So this is different than finding a well. So you're talking about finding existing CVEs or doing the research to find new ones?
Yeah, I mean new ones, because like I assume that fuzzing can reveal some inputs that were not validated, and that can trigger some critical path. Yeah, and that's one thing why we're looking at the CI processes, because anytime you do something that is security focused in an open source project, what you want to make sure you're doing is detecting issues and not publishing 0 days. So you have to be a little careful about how you roll the stuff up. But we do have an interest in doing more of that kind of automatic work. I think because it's more of a unit test idea, it's more on the individual developer side to do this sort of thing as part of their, you know, check-in process. I wouldn't necessarily expect someone to check in a version of their code into, say, the EK2 trunk that's got these functions stubbed in, but they might have it in an internal GitHub branch that they're using before they push it to main. Yeah, there is a. So if we consider, for example, Minnow board building process, and that we can take some pieces, some open pieces, so you can wonder when you're releasing any binary based on that, or min platform when you're releasing something based on that, that you want to use this tool. And so what's the path if you find something? Yeah, well, I mean, the path if you find something is already established. There's 2 ways of submitting bugs into Tiano Core. One is I have standard functional bug, and that's just the regular Bugzilla process. And then there's an InfoSec team that works on a non-public version of that Bugzilla. If you enter something and flag this as a security bug, you can't see that BZ unless you're part of the InfoSec group. And that allows security researchers and developers from a variety of the Tiano Core contributors to take a look at it and see if it's a security issue. They go down the path of treating it as a regular security issue. So it goes into some kind of, if it's the appropriate company has a bug bounty program, we push it into their bug bounty program and treat it as a coordinated disclosure issue. So again, we're not going to use our Bugzilla as a 0-day database. But one thing that I do want to point out, the reason why it's harder to just slap this instrumentation in, like if it was just a, automatic, patch to throw these 3 functions in, it would be really easy to put that into the CI. But because you're dealing with things that touch hardware, sometimes the stubbing process, like the way that you would stub these functions in a USB driver is different from PCI, different from something that's purely software logic. So we haven't quite got to the point where we can just say, oh, this is the USB set of stubs versus this is the PCI set of stubs, right? If we get to that point, then it might be more of a snap-in type of environment.
Yeah, question from my side.
Yes.
You already mentioned science. I know that people, for example, at the University of Bochum, they do a lot with fuzzing. Have you approached any researchers? Have they approached you, or how's the academia perception here?
Right now what we're doing is taking the output of academic work, because a lot of these fuzzers are university projects or quasi-university projects. Intel has a group called Intel Labs that is sort of our science fair experiment group, and some of our tools that are adjacent to this, things that we've done that involve fuzzing or weird unit test cases, have come out of labs projects. I don't know if you want to.
To some researchers from that university. I think a lot of them are very focused on KEFL. That's something that we're looking at adopting in sort of a parallel project to this.
Yeah. Okay, my mystery guest introduce himself.
Hi, I'm Brian Delgado. I work at Intel. I'm on the Excite project, which also does firmware fuzzing.
Yeah, so he's my stunt Brian. All right, how much time we got left for questions?
We still have a few minutes, so.
Is this something that we can tear up and use for other architectures relying on EDK2 or other operating systems?
Sorry, could you repeat the question?
Is this something that we can port to other architectures based on EDK? I mean, that are running EDK2 on their platforms
absolutely.
or other operating systems?
There's nothing in here I'm aware of that's an architectural limitation because and that's another reason why we didn't Intel brand it. If we stuck an Intel trademark on it, even if it would work across architecture, it would probably make some people think twice before they did. Honestly, I'm a rising tide, raises all boats kind of mentality in open source. If you find bugs in a non-Intel architecture, it's likely that it impacts an Intel architecture because you're testing cases that we can't do in our architecture. So I'll give you an example. Lenaro found this really nasty bug with memory mapping. So it turns out that if you make an array and you can't count, you get null pointers. Null pointers in Intel architecture point to 0:0 in old memory terms. That's where our interrupt 0 handler lives because we put the interrupt table down at the base of memory and we boot from 1 megabyte because it was the 80s and people were doing a lot of weird things. So it turns out in ARM architecture, and I didn't know this until last year, you don't have to have physical memory at base address 0. And a lot of platforms don't. Why? I have no idea. But if you, say, take an NVIDIA card, just as an example, and use its graphics driver, it'll work great on Intel, but it doesn't work so well on ARM, right? So what they did is they built this weird emulator package. There's a FOSDEM presentation from a couple of years ago. This is really cool. And they essentially run QEMU in memory. And whenever they hit an instruction that's not in the native instruction set, instead of invoking the non-execute bit handler, it invokes QEMU and runs the OPROM in an emulator so that you can run Intel OPROMs on ARM architecture. And it's a proving ground thing. They don't, they may ship it, but they probably shouldn't. But it's just a proving ground piece so they can test more cards. Well, you get a null pointer in that graphics output protocol, and on our platform, it would just look like garbage data at the bottom of the array. In their platform, it dies. It halts and catch fire. And then they actually see that, oh, this GOP driver for x64 has a bug in it. And so ARM reported that bug back to the manufacturer on our platform architecture. We would have never found that bug. So yeah, go run it on something that we don't make, see what happens, check it in.
Yeah, I mean, I'm coming mostly from an embedded platform perspective. Like I want to port it down to like something like RISC-V. It's been widely talked about conference. And,
yeah, absolutely. And again, that's why it's an EDK2 staging. Go ahead and play with it, contribute it. And definitely if you work on this stuff, don't just check the code back in, check the test cases in. Because again, you want to be able to prove your work. It's a math class in this case.
All right, then thanks again.
All right, thank you.